So last time we saw how we could solve this system of differential equations that arose from this natural circuit using a magic whisper. And we solved it out just writing things out in terms of systems of equations. We didn't really use the matrix vector style at all. So before we figure out how we could possibly discover such changes of coordinates by ourselves instead of having to wait for someone to whisper them to us, it's useful to take a matrix perspective on what just happened. So notice that we had this change of coordinates, which we can write in vector matrix form in the following way. We will write u1, u2, the vector, equaling some matrix times v1, v2. So what is this matrix? Well, u1 equals 0 times v1 plus v2. u2 equals v1 plus 2v2. So we have this matrix that represents how you get from v1, v2 to u1, u2. Great, that's nice. So, how do we go the other way? Well, we know how to do that. We know that by means of the matrix inverse, this is clearly an invertible matrix, we can go back. So what is the matrix inverse here? Well, quick calculation will reveal that this minus 2, 1, 1, 0 is the matrix inverse. It's good to check. Minus 2, 1 times this is 1. Minus 2, 1 times this is 0. 1, 0 times this is 0. 1, 0 times this is 1. So this is indeed the inverse. So we have this way of going back and forth between u's and v's. So in this picture, given that we have a way of going back and forth between u's and v's, we can now take this differential equation and use this. Use this changes of coordinates to get this in terms of u's. So what do? We say d by dt u1, u2 equals 0, 1, 1, 2 d by dt v1, v2. Why can we do this? We can do this because taking a derivative is linear. It kind of plays nicely with things like matrix multiplications and scalar multiplications and so on. So it just commutes nicely. So this goes in and this hits v1, v2, but we know what this is. This is 0, 1, 1, 2 times, parentheses, everything here, minus 5, 2, 2, minus 2, v1, v2, plus, if you want to keep track of everything, 3, 0, v in. So we have this, and now we also know what v1, v2 is. That's given by this, so we can get everything in terms of u's. 0, 1, 1, 2, minus, minus 5, 2, 2, minus 2, minus 2, 1, 1, 0, u1, u2, plus 3, 0, v in, which we can grind out, and I won't bore you with the details of the matrix multiplication here. It's good for you to do it yourself. This will turn into, so this matrix times this matrix times this matrix becomes minus 6, 2, 0, minus 1 times u1, u2. And this 3, 0 times this clearly just becomes 0, 3 v in. So now you see how we have d by dt u1, u2 in terms of this. So if you look at this matrix, remember, we were able to solve it. Is there something about the structure of this matrix that tells us that we will be able to solve it? Why, yeah, there is. The bottom row is scalar, right? d by dt u2 equals minus u2. And then notice that we can just take this and push it up and substitute it. So you saw this in Gaussian elimination. When you did Gaussian elimination, after you finished doing the downward pass, what happened? You were left with a matrix that was upper triangular. What do we mean by upper triangular? It means that everything below the diagonal of the matrix is zeros. All the action is in the upper right triangle. That's what we call upper triangular. Upper triangular matrices, it means that we can solve for the bottom differential equation, that'll be scalar, then we can back substitute. We go take it up and then repeat. Again, we'll get a scalar differential equation. We can solve it and keep going. So what we're looking for is a way of getting ourselves into forms that are upper triangular or nicer even than upper triangular. So that's the goal. That's the kind of form we would like to form. We would like to find automatically using properties, presumably, of the matrix 5, 2, 2, minus 2. That's what we'll talk about next.